So welcome. In this class, we are going to discuss about some set operations. So we'll give some definitions and examples on set operations. And then in the subsequent session, we'll be discussing about how we use knowledge on set theory to help us do some counting problems. So let's begin by set operations. So to start us off, we will define a universal set. And a universal set is usually denoted by U with a small tail to differentiate it from another operation we call union of sets. And this is simply a set which contains all elements under consideration. This is a set that contains all elements under consideration. It is also called the universe of discourse or simply the universe. So for instance, if one considers a set of men and women, then we can say a universal set is probably the set of human beings. Because when you say human beings now, it will take care of men and women. And then if one considers sets such as pigs, cows, chicken, horses, dogs, cats, then a possible universal set is probably the set of animals, or we can say domestic animals. And if we have, for example, this set A given by 1, 2, 3, and we have B given by A, B, 3, then possible universal set is this set 1, 2, 3, 4, A, B, 3, or I can say 1, 2, 3, A, B, or I can say even U equals to 1, 2, 3, 8, A, B, X, Y. Now, the key thing is that here we have the set A and set B as our sets under consideration. And A has 1, 2, 3 as the elements. B has A, B, and 3 as the elements. So what we refer to as the universal set with respect to these two sets A and B will be any set that will be containing all the elements of set A and all the elements of set B. Whether the set will be having other extra elements that cannot be seen in A and B at the same time, that doesn't matter. What matters is that all that you can see in the listing of A and the listing of B should be seen in the list of that other set that will be referred to as the universal set. So all these are other possibilities of the universal set. So which means that universal set is not unique for some given scenarios. So for instance, all these other three qualifies to be called the universal set with respect to the set A and B. And then in a Venn diagram, and a Venn diagram is simply a picture we use to represent sets. So in a Venn diagram, we usually use a rectangle to denote the universal set. So I mean that to show universal set, we will be just drawing a rectangle and then we label it as U. So having understood the concept of a universal set, which is simply a set that contains all elements under consideration, then let's define another term related to sets operation we call complement of a set. To define complement of a set, you need the universal set and another set, say A. So let U be the universal set. And A be any other set which obviously is contained in U. So the complement of A denoted by, so we write A, then power C, or we can write A, then we put a bar on top, or we can write A, then we put a prime, is a set containing all elements in U, but not in A. So symbolically, we can write this as A complement is a set of all elements X, which are in the universal set, such that these elements X are not in A set. We can draw a Venn diagram to really illustrate this concept clearly. And this is what we have. So if this is our universal set, so this is our universal set. Within this universal set, let's have set A. So when we say complement of set A means all elements which are contained in the universal set, but not in A. So it means that we shade outside A. So this so this is what we call complement of A. In simple terms, means you are not in A. So the shaded region is what defines A complement. So another example, given A is a set 1, 2, 3, and B the set A, B, C, and say C is a set 1, 3, then, and we have a universal set 1, 2, 3, 4, A, B, C, D, then A complement means we pick all the elements which are in this universal set U that are not 1, 2, and 3. So we'll have 4, A, B, C, D. And if I were to define B complement, means we pick all the elements in the universal set that are not A, B, and C. We'll have 1, 2, 3, 4, D. And then C complement will mean we pick all elements in U which are not 1 and 3. So I have 2, 4, A, B, C, and D. And whenever the element in the set and its complement should constitute the whole universal set. So our universal set, for instance, has 1, 2, 3, 4, 5, 6, 7, 8 elements. So the number in A complement should be a set with 5 elements because A already has 1, 2, 3. So that when we add, we get the total number of elements in the universal set. So 1, 2, 3, 4, 5. So 5 plus 1, 2, 3 is 8, which is an agreement. And then B has 1, 2, 3. So B complement should have 5 so that when we add, the total should give you what we have in the universal set. And C has 2 elements. So the elements in C complement must be 6 so that when we add them, we get the total number of elements in the universal set. So another operation is what we call union of sets. So we define, let's have some two arbitrary sets. So let A and B be two sets. The union of A and B usually denoted by is a set containing all elements in A or in B or both in A and B. So symbolically, we can write A union B is a set with all elements X such that X belongs to A or X belongs to B or those elements X are in both A and B. Similarly, we can define the union of three sets A, B, and C. So A union B union C will be the set with all elements X such that X belongs to A or X belongs to B or X belongs to C, and even possible common elements which are to the three sets. And in general, if A1, A2, A3 up to AN are sets, then their union is a set of all elements which belongs to at least one of them. And we write A1 union A2 union A3 union AN, which can just be written as I1, then AR. So which simply means that I starts from 1, 2, 3 up to N. To have a better feeling of what the union of sets is, we can draw a Venn diagram. So this is our universal set. So let's set A be given by this blue circle, and let set B be given by red circle. So I want to represent A union B. Now, this drawing has 4 regions within the rectangle. We have, if I call this 1, this 2, this 3, this 4, then by definition of A union B means you are either in A, and A is given by the blue circle. So it means that you are either in 2 or 3, or you are in B. So if you are in B means that you are in the red circle. So, and that is represented by 3 and 4, or even both the sets, which is part 3. So then to show the set A union B in this diagram simply means that we shade every region within the blue and the red circle. So we'll have this. So that's what represents A union B. And then let's also draw a diagram that represents the union of 3 sets, A, B, and C. So this is the universal set. So let this be A. Let this be B. And let this be C. So A union B union C will mean that you are either in the red circle, or you are in the blue circle, or you are in the purple circle. And even points where those circles meet. So which means then that region will be anything within the circles. So that's what we call region A union B union C. So just a caution, when you have been asked to represent, say, the union of three sets A, B, and C, some people may do this. So this Venn diagram will not be accepted unless in the question itself, there's enough information to show that A and C are not sharing some elements. But unless you see that information clearly in the problem, if you draw your three sets A, B, C as in this diagram, then you get it wrong. You only do that one if there's clear information that A and C share no elements. But unless otherwise that information is given, you draw all the three circles touching each other. Another operation is what we call intersection. So intersection, we use this sign. So let's A and B be two sets. Let A and B be two sets. The intersection of A and B denoted by is a set containing all elements common in A and in B. So that's to say, A intersect B is a set of all elements X such that X belongs to A and at the same time, X belongs to B. Similarly, if we have three sets A, B, and C, then the intersection will be the set containing all the elements X such that X is in A and X is in B and X is in C. That those elements must be seen in all the three sets under consideration. And in more general, if A1, A2, A3, up to AN are n arbitrary sets, then the intersection is the set containing all elements common all the sets. It is denoted by A1 intersect A2 intersect A3 up to intersect AN, which can just be written as intersection from I1 to AN of AI. So let's draw a Venn diagram to see how we can visualize intersection of two sets A and B. So in this, we'll draw the intersection of A and B. And in this other diagram, we'll represent the intersection of A, B, and C. So let this be A, that be set A. Let this be set B. Let's have set C. So remember the definition of intersection. We have said is a set that contains all elements common to the sets under consideration. So for the first diagram, elements common to set A and B will be the region where the red circle A meets the blue circle B. And this will be the part. So this is a part that shows where the two circles A and B meet. An intersection of A, B, and C means where the red circle A meets blue circle B and also meets green circle C. And this will be the part. Remember, this was this is a region where all those 3 circles meet. So please note that if intersection of A and B is empty, then we say that A and B are disjoint sets. So whenever the intersection is an empty set, that means that there's no common element, then the sets are described as being disjoint. And you can represent them on a Venn diagram. So this is U. This is set A. And then we have another set B. So in this example, A and B are disjoint. So meaning that there's no common element between the two sets. And in a similar manner, you can draw a diagram to show 3 disjoint sets A, B, and C, and even n sets which are disjoint. So as an example, given A is 1, 3, 5, B is 1, 2, 3, 4, 6, 8, C is 2, 4, 6. Find one, A intersects B, 2, A intersects C, 3, A union B, 4, A union C, 5, A intersect B, intersect C, 6, A union B, union C. So to define A intersect B means identify elements common to A and B. And we can see that 1 is common to the two sets, 3 is also common to the two sets. So this will be a set having 1 and 3 as the only elements. Then A intersect C means what is common to set A and C. So A and C, 1 is in A can be seen in C, 3 is in A can be seen in C, 5 is in A but can be seen in C. So this will be simply an empty set, or you can write it as A union B means you are in A or you are in B, or maybe even both in A and B. And it's the easiest set to write. Just write all the elements of the first set, 1, 3, 5, then join to the elements of the second set. But things which you have already written, you don't have to repeat. So 1 has been written, 2, and then 3 has been written, 4, 6, and then 8. Remember, when you are listing elements in a set, order does not matter. So you may rewrite the numbers or leave it the way they are, still fine. A union C, let's write all the elements of A, 1, 3, 5, then join to the elements of C, 2, 4, 6. Then A intersect B intersect C means what is in A at the same time is in B, at the same time is in C. But already we have seen that A and C share no common elements. So which means all the three sets cannot have any other element which is common, because already two of them have nothing in common. Then A, and B, and C, we write all the elements of A, 1, 3, 5, joined to the elements of B, avoiding repetitions. So we have 1 has been written, and 2, 4, 6, 8, and then elements of C, all of them have been written. So this would be the complete set. So another operation is what we call set difference. So we show it by a normal minus sign. And we need two sets. Let A and B be two sets. The set difference or relative complement of A with respect to B, usually denoted by A minus B, is a set of all elements contained in A but not in B. So if we want to be more technical, then we can say A minus B set of all elements X such that X belongs to A and X does not belong to B. So means you must be in the first set, but not in the second set. So similarly, B minus A would be the set of all elements X such that X is in B, but X is not in A. As usual, we draw a Venn diagram to see how we can interpret these two sets, these sets A minus B and B minus A. So this, let this be the universal set. So here I'll represent A minus B, and this other side, let's represent B minus A. So I have this. So my A, I have this. It's my B. Okay, let me just call it yes, my yes, be still A. And then let this be B. Let this be. So A minus B means you are sitting in A, but you should not be counted to be in set B. So here it means that A minus B, you are in the blue circle, but you should be in a part or within blue circle such that you shouldn't be counted to be in red circle. And this would be the only part of A. So that is what we have as A minus B. Then for B minus A means you are in the red circle, but you shouldn't be counted to be in the other blue circle A. And this will be the only part. So that is set B minus A. So if, for example, A is 1, 2, 3, 4, and B is a set 1A, B, 4, and C is a set 1, 4, 3, 2, then when I say A minus B, I mean elements which are only in A, but cannot be counted to be also in set B. So 1 cannot be part of that set because 1 is in B. 2 would be part of that set because 2 cannot be seen in B. And then 3 is also part of this A minus B. 4 will not be part of A minus B because 4 can be seen in B. So A minus B will be having only 2 elements, 2 and 3. And then A minus C means all elements which are in A but not in C. 1 is in C, so 1 cannot be part of that. 2 is in A, so 2 is in A and also in C, so it can be part of that set. 3 is in A and is also in C. 4 is in A and is also in C. So this would be an empty set. There is no element in A which cannot be found in C. And then B minus C, A, 1 cannot be part of that because 1 is in C. A, yes. And then B, those be the only elements. And then C minus B will be, you are in C but not in B. 1 can be part of that, 4 can be part of that, 3, yes, and then 2. And then B minus A, elements which are in B but not in A will be A and B alone. And then next operation is what we call symmetric difference. Symmetric difference of two sets. So we require two sets. Let A and B be two sets. The symmetric difference of A and B denoted by or some people denote it as is a set of all elements contained in A or in B, but not both. So it means that you should be either in set A or in set B, but you should not be counted to be both in set A and set B at the same time. So this is to say the symmetric difference of A and B, the set of all X such that X is in A or X is in B, but not both. So in a Venn diagram, we'll have, if this is set A and this is set B, then A is this circle. And so to be only in A, so remember we'll avoid this part, which is common to A and B, and then shade these other parts. So the shaded part is what we call the symmetric difference of A and B. So you are either in A or in B, but you shouldn't be counted to be in both sets. And if you remember what you have done in the set difference, you clearly see that if you take A minus B, you join to B minus A, then you'll have this symmetric difference of A and B. So note that the symmetric difference of A and B is the same as A minus B union B minus A. Remember, when you are dealing with sets joining, the operation union is the same as, from layman's point of view, you are joining, and intersection simply means common. So when you join A minus B to B minus A, you get this set symmetric difference of A and B. And if you check the shadings for A union B and A intersect B, you can also all these shadings are for A union B. If you remove the middle part, then you get the symmetric difference of A and B. And the middle part is what we call A intersect B. So another way of interpreting A symmetric difference to B is saying that get the A union B and then remove, subtract A intersect B. We'll be defining the same set. So if I give you, for instance, let A be the set 1, 2, 3, 4, and B be the set 1A, B, 4, then A minus B is going to give me 2, 3. B minus A is going to give me A, B, if you follow the previous discussion. So which tells me that the symmetric difference of A and B in this case should be A minus B joined to B minus A, which will be 2, 3, A, B. If we were to determine A intersect B, then you see that I will have 1 and 4. That's what is common to A and B. And A union B will be 1, 2, 3, 4, A, B. So when you say A union B minus A intersect B, so all these elements without 1 and 4 will be 2, 3, A and B, which is the same set we have gotten in this given case. And always note that in the previous case when we were discussing about set difference, that for any arbitrary sets A and B, when you say A minus B union B minus A, you get the symmetric difference of A and B. And when you say A minus B intersects B minus A, then it will always be an empty set. So A minus B and B minus A will never have common elements, or simply common elements are 0. And then last but not least, is what we call Cartesian product. The Cartesian product of sets. We use the normal multiplication sign. So let A and B be any two sets. Then the Cartesian product of A and B denoted by is a set containing all the ordered pairs such that the first element is from the first set and second element is from the second set. So you can write this as A cross B, the set of all ordered pairs AB, such that A is in A and B is in B. Similarly, B cross A, or Cartesian product of B and A, will be the ordered pairs A, B, A, such that B is from B and A is from A. So for example, given A is the set 1, 2, 3, and B is the set A, B, C, then A cross B will be the set. So you will be picking, you'll be writing pairs such that the first elements are from A and second elements are from set B. So we start by 1 pair with A, 1 pair with B, 1 pair with C. Then go to 2, 2 comma A, 2 comma B, then 2 comma C. And lastly, 3 comma A, 3 comma B, and then 3 comma C. So that will be the complete set of A cross B. And if you write B cross A, now your starting elements would be from set B, which will be A comma 1, A comma 2, A comma 3, then B1, B2, B3, then C1, C2, and then C3. So clearly you can see that cardinality of A cross B, the number of elements here is 1, 2, 3, 4, 5, 6, 7, 8, 9. And cardinality of B cross A is 1, 2, 3, 4, 5, 6, 7, 8, 9 also. So we can say A cross B is equivalent to B cross A, because they have the same cardinality. But the two sets are not equal. Note that A cross B is not equals to B cross A, since they all have different elements. Please note that an element like 1 comma A is not the same as A comma 1. You just like, if you are plotting points in the Cartesian plane and you plot. So this is your X, Y axis, say 1, 2, 3, this X. Say this is 1, this is 2, this is 1. So this point, for instance, is a point 2, 1. And then if I plot this point, this is a point 1, 2. So you see 2, 1 is a different location from 1, 2. So an element like 1, 0, 1A and A1 are not the same. So the Cartesian product of A and B is different from the Cartesian product of B and A. So which means that order matters in how you are writing the elements of these two types of operations. Then lastly, power set. So let A be a set the power set of A denoted by is a set containing all subsets of set A. So e.g., if A equals to 1, 2, then the power set of A will be the set having the elements. So remember, these are sets with two elements. So the subsets can either have the two elements or one element each, or no element, where we get the empty set. So the subsets of A will be set having no elements, the empty set, or a set which has one element each, which can be formed by 1 or can be formed by 2, or you can have the whole set formed by the two elements of A. And you can see that here, cardinality of power set of A in this case is 1, 2, 3, 4. Is 4. And then if we have another set B with elements 1, 2, 3, then power set of B would be given by, so these are set with 3 elements. So you expect the subsets to be having either the 3 elements or the 2 elements each, or 1 element each, or 0 element each, the so-called empty set. So 0 elements will be the empty set. 1 element each will be formed by either 1, or we can form by 2, or we can form by 3. Then 2 elements, subset with 2 elements each will be formed by either 1 and 2, 1 and 3, or 2 and 3. So these are the only possibilities for having pairs when we have only 3 elements to choose from. And then we can either have the whole set. And here, power set of B, cardinality will be given by 1, 2, 3, 4, 5, 6, 7, 8. And it has been proven that if you know the cardinality of the set A, then you can know the cardinality of the power set of A by this formula. So given that cardinality of A is n, i.e. cardinality of A is given by n, then the cardinality of power set of A is given by 2 power n. So when I know the number of elements in a set A, I should be able to know the number of elements in the power set of that A. So e.g., a set C, which has a B, C, D, has cardinality of the power set of this C will be 2 raised to power 1, 2, 3, 4, which will mean 16. So you have a set having 4 elements, then the number of elements in its power set will be 16. So if we have D having A, B, C, D, E, then the cardinality of the power set of D will be given by 2 power 5, which will be 32. So in some problems, you will be given the cardinality of a set, and then they ask you to find the cardinality of the power set. So the formula that relates the power set and the cardinality of the power set and the cardinality of the set in question is given by this relation here, where n is the cardinality of set A. So from that formula, you can get any unknown provided that you have been given one. Either you can get the power set of the cardinality of the power set, or you can get the cardinality of the set in question if you have the value for the cardinality of a set. And then generally, a set is always a subset of itself. So this I mean that for any set A is a subset of A. And then number 2, the empty set is a subset of any set. That's to mean that empty set is always a subset of any arbitrary set C. So the next session will be discussing about the application of operations on set theory to counting problems. Thank you.